example of finding a volume of a solid of revolution. Here I want to find the volume of y equals 0, y equal the natural log of x equals 0, and y equal 2, that region bounded by those curves, and revolve that around the y-axis. Now I've started the graph. First, y equals 0 is the x-axis. So I have the x-axis. Y equal the natural log of x. I've graphed y equal the natural log of x here. X equals 0 is the y-axis. And then y equal 2 is a horizontal line at y equal 2. So remember, it was the x-axis, y equal the natural log of x, y equal 2, and the y-axis. So the region that we're talking about revolving around the y-axis is this region caught between those equations, those graphs. And I'm revolving it around the y-axis. So remember that showing the axis of revolution is just kind of making the loop around the axis so you can envision it. So here, this region is spun out and around about the y-axis. And I see that the shading is against the axis of revolution throughout the whole interval. So this is one that possibly I could do by the disk method. Now if I want to do this by the disk method, I need to make my segments that I cut, these sections, to be perpendicular to the axis that I'm revolving it around. So think about making these little cuts throughout the region, because they need to be perpendicular to the axis you're revolving it around. Well, if I do that, then the thinnest part of that is with respect to the y-axis, the differential dy. So this is going to be a dy. And it is a disk because it is against, the region is against the axis of revolution throughout that. And so our volume, remember, is pi times the integral from the start of the region to the end of the region. So as I go from bottom to top, since I'm doing the horizontal subrectangles, I want the y value, so it's from 0 to 2. And then square the radius, and then dy. And the radius is reaching from the y-axis out to the curve. That's written to start with as y equal the natural log of x. Well, this is the horizontal movement off the y-axis over. So what I need to do is make sure I have this y equal the natural log of x solved for x. I need it as x in terms of an expression in y's to be able to put it into this equation with the differential dy. And also, this is the x movement, so I need to know what x is equal to. Well, if I have y equal the natural log of x, remember natural log is a base e. So when we want to write this from the logarithmic form to the exponential form, my base is e, my exponent on my base is y, and that is what x is equal to. So, solving this for x is equal to e to the y. My x is equal to e to the y is my radius. That's pretty much the hard part of the whole scenario, is getting this set up and deciding what method it is that you want to do to solve it. Okay, let's go through the rest of the specifics about the solution process. Here I have an exponential expression raised yet to another power. And remember, when you take an exponential expression to yet another power, you keep the base and you multiply the exponents. So this volume is pi times the integral from 0 to 2 of e to the y times 2 is 2y dy. Now to integrate this, I need to do a u substitution. So if u is equal to 2y, the expression that's kind of the plug-in of it, then du is equal to 2 dy. And I have my dy, but there's no coefficient of 2 here. So I'm going to divide both sides by 2. So 1/2 du is the replacement for dy. So once I come back to my integral, I have pi times the integral y equals 0 to y equal 2. We're going to write it like that when we go to use, just to remind ourselves not to plug in these numbers until after we transfer back into the y's. So this is then e to the, well, 2y is u, times, and dy, when I take out dy, it's equal to 1/2 du. Okay, so next up, this is a multiplication of a constant, 1/2. So I can bring the 1/2 constant factor out in front. So that's volume times pi over 2, because remember, pi over 1 times 1/2 would be pi over 2, times the integral from y equals 0 to y equal 2 of e to the u du. Well, the integral of e to the u du is just e to the u. And we're evaluating that from y equals 0 to y equal 2. And then we want to put the 2y back in for the u. So I have pi over 2 times e to the 2y evaluated from 0 to 2. And when I then evaluate it, I'm going to put in the 2. Remember, put in the top endpoint, upper limit of integration, minus plug in the bottom. So that's pi over 2 times e to the 2 times 2 minus e to the 2 times 0. Well, e to the 2 times 2 is e to the 4. E to the 2 times 0, well, 2 times 0 is 0, and e to the 0 is 1. So this comes out to be pi over 2 times e to the 4th minus 1. And this is approximately equal to 84.192 cubic units. And so here's an example of finding your volume of your solid of revolution using the disk method if you're revolving it around a vertical axis of revolution.